everyone! This is a second part of the video about symmetry elements and symmetry operations. So far we have talked about rotations, reflections, and the identity operation. And ahead of us we have improper rotations and inversion. Let's come back to the main slide with all the symmetry operations for tetrachloroplatinate 2. S refers to improper rotation and I to inversion. We will do them pretty much simultaneously because in fact inversion is a special case of improper rotation, similar to squares being a special case of rectangles. So here we have some rectangular prism and we'll be doing symmetry operations on it. Let's focus only on the vertices and let's color one vertex in a different color so we see more clearly what is going on. So what is the operation of improper rotation? It is a rotation around an axis followed by the reflection in a plane perpendicular to the axis. So it's a composite operation. Regarding the symmetry element, you would think that it's the axis that we use for rotation and the reflection plane, and technically it is, but chemists call the symmetry element of improper rotation a rotation-reflection axis, and it is only the axis that is usually drawn on diagrams. The same as in the case of normal C rotations that we already know, a rotation-reflection axis, Sn, generates multiple operations, and again we need some nomenclature to tell them apart. S and m is the operation of rotation by m times 360 divided by n degrees, followed by m reflections in the perpendicular plane. So the improper rotation that we see is S for 1, rotation by 90 degrees followed by 1 reflection. What would S for 2 look like? Let's bring back the body of the prism so that we can track the motion easier. So S for 2 would be rotation by 180 degrees followed by 2 reflections. And we would write it down as S for 2 equals C for 2 dot 2 sigma. The dot indicates operations following one another. It doesn't matter in what order we do the operations that the improper rotation consists of. Rotation first, followed by the reflections, or the other way around. Or if we do it stepwise, rotation, reflection, rotation, reflection, we always get the same result. And you might say that what we have just shown is obvious, and it is, but please notice that often when we take some arbitrary two operations and do one after the other, the result is not equal to what we would get if we did the operations the other way around. We have already said that the rotation-reflection axis generates multiple operations. Let's think how many operations it can generate. In other words, after how many operations we return to the initial configuration. Let's look at the rectangular prism. It is obvious that after 4 90 degrees rotations and 4 reflections, we come back to the starting configuration. However, if we take a triangular prism, then after 320 degrees rotations and 3 reflections, we don't reach the initial configuration because of the odd number of reflections. So we need to keep going, and after another 3 rotations and 3 reflections, we do arrive at the starting configuration. It's because now we have reached an even number of reflections, 6. Knowing that, please pause the video and write down all the symmetry operations generated by the following rotation-reflection axis. Okay, that was easy. Now let's think which of these operations are unique. We cannot reduce the mn as if it was a fraction, because we would lose the information about reflections. Here is an example of S for 2 not being equal to S to 1. I will give you another example. Let's take BH3 and do S31 on it. It appears that the result is the same as if we did C31. But if we track the effect of symmetry operations on boron p orbital, then the orbital would have opposite phase, so please don't forget the reflections are there. Now it's a good time for you to pause the video and decide which of the operations are unique. Please break up the improper rotations into rotation and reflections, and remember that an even number of reflections cancel out. Okay, when you simplify whatever you can, and you still get a composite operation, then that improper rotations are unique. So in most of the time, improper rotations are unique for an odd number of reflections. However, here we see S33 and S55, where we have a full rotation and an odd number of reflections, so the overall effect is that of a sigma. So I hope that you got it right. Now, there is one case where you might have gone wrong because it's something that we haven't done yet. C21 dot sigma equals inversion. So now we are going to move on to inversion, which is the last type of symmetry operation. As we have just said, the symmetry operation of inversion is a special case of improper rotation. It's S21, rotation by 180 followed by reflection in a plane perpendicular to the axis. Please notice that the pink vertex ended up exactly in the opposite corner. So if we set the center of the structure at 0, 0, 0, and that is convenient and sensible thing to do, then our pink vertex goes from x, y, z to minus x, minus y, minus z. To go directly from x, y, z to minus x, minus y, minus z, obviously we need to go through the point at 0, 0, 0. The point is called the center of inversion or the inversion center, and it is the symmetry element associated with inversion. So symmetry operation of inversion is usually not animated in 2 steps as rotation by 180 and reflection, but in 1 step. All the atoms are moving along straight lines through the center of the structure and continue the same distance and direction out the other side. It might seem that inversion is cumbersome to spot, but it's not. Simply the atom at the center, if there is any, does not move, and all other atoms occur in equivalent pairs which interconvert. Let's demonstrate it once again, but this time on tetrachloroplatinate ion. I even painted all 4 chlorines with different colors so that you see that the atoms interconvert pairwise and the middle platinum atom stays put. Let's look at some other examples. Staggered ethane does have an inversion center. Under the operation of inversion, HA swaps with HD, and so on. It might be useful for you to know that molecules which have an inversion center are called centrosymmetric. And here we have an example of a structure that doesn't have an inversion, tetrahedron. Tetrahedron is a structure that, for instance, methane is based on, and we can see that if we reverse the sign of hydrogen coordinates, then the tetrahedron ends up upside down, which is not an equivalent configuration. So that's all I have for you about inversion. The bottom line is that if you forget some things about inversion, you can always recall that inversion is S21 and perform the operation of inversion in 2 steps. Now let's do some exercise. We already know that a methane does not have S21, that is inversion. Does methane have any other improper rotation? It might be helpful to draw a methane in a cube or use 3D models. For instance, use a molecular model kit. Methane does have S for rotation-reflection axis. Please notice that it doesn't have a C for rotation, nor a reflection, but if we combine these operations, then we get to an equivalent configuration. Rotation reflections might not be the easiest to spot, however, let's notice some trends that might help you. Any molecule which has CN axis and the mirror plane independently will have an improper rotation. There are many structures of molecules that we could use as an example, but let's focus on molecules that are based on regular polygons. They can be flat, for example SO3, a regular triangle, or for example xenon pentafluoride anion, regular pentagon, or they can be made of 2 eclipsed polygons. Here we have a model of eclipsed ethane. The structure can be simplified to 2 eclipsed triangles, or more precisely, a triangular prism. And here we have a model of eclipsed ferrocene. The structure is made of 2 pentagonal ligands, C5H5-, and an ion cation, Fe2+, is sandwiched in between them. Now, there are cases where a molecule doesn't have a principal axis or a mirror plane perpendicular to it, and still it has improper rotation, as we have seen with methane. I cannot give you a rule for all, but there is a type of molecules based on exactly staggered regular polygons which fall into this category. An example of a molecule that is based on 2 staggered pentagons can be, for instance, staggered ferrocene. We can see that the structure has S10, HA goes to HB, but it only has C5, HA goes to HC. It does not have C10, it doesn't have a horizontal reflection plane either. An example of a molecule that is based on 2 staggered squares can be, for instance, this nickel complex. The squares are cyclobutadiene ligands. An example of a molecule that is based on 2 staggered triangles can be, for instance, staggered ethane. If we take one vertex away from a triangle, we end up with a line. Methane could be described as 2 staggered lines, if you look at the molecule from the top. That begs the question what molecule can be described as a line. For example, ethine or ethene would also do. The last thing on the slide, let's spot some regularities about inversion for these 2 groups of molecules. So for the top group, the molecules that are based on polygons with an odd number of vertices have no inversion, because no 2 vertices are opposite each other. However, the molecules with an even number of vertices do have an inversion. The opposite is true for the bottom group of molecules, due to the staggered character of the structures. Now let's have a last look at the complete list of symmetry operations for D4H symmetry. 2s4 refers to s41 and s43 because they are unique. Also, please remember that inversion is s21 and it does not come from s42. S42 simplifies to c21 as we explained earlier. Now the final two questions. Please notice that benzene can be simplified to a hexagon, and please remember about reflections when performing improper rotations. You might for instance use an arrow to mark the up and down direction. In few seconds I'll show you the answer. The slides from the video will be below. Thank you for watching, bye!